Hey folks, well, this will be most of the last content before we get into the review mode here. So we still got about another week and a half, maybe 2 weeks left, depends on how much stuff we put together on this particular last segment of information that we present for you guys. Those of you who will be sticking around after the AP exam is over and after the seniors get out of here, we will have a brief tour through some electricity and electric circuits, just because I know several of you are going into AP Physics 2 next year. So that'll give us a jump start on some of those concepts. But anyway, we're still got half of Unit 8 left, so this will be content starting for Quiz 8B. So like I said, it's not a ton of content, and there's a few things I'll cut out that we don't need to know, but a lot of this stuff is going to be in Physics 2, and so I'm going to make sure that we have it. Now, as far as the AP exam this year is concerned, this information is not on this year's AP exam, or at least it's not supposed to be. So we should be able to cut this down and make it go fairly smooth. There will be a few little lumps in the road, I'm sure, but we'll try to get this across to you as good as possible. All right, so what we're going to be getting into is mechanical waveforms. I know a lot of you guys that are in college chem have been talking about electromagnetic waves, and we're just going to focus on just the mechanical waves. So when we're talking about a mechanical wave, this is the vibration in matter that transports energy. So once again, that's one of the big differences between a mechanical wave and electromagnetic wave. Electromagnetic wave, like light we get from the sun, does not need a medium to propagate through, whereas all mechanical waves are going to require some sort of medium. So basically, as the energy is moving through the waveform, you will have the wave displace some portion of the matter that is associated with that wave, whether it's vertical up and down while the wave moves right and left, or in the same direction that the wave propagates, which we'll talk about those terms here in a little bit. So just making sure we all are on the same page on some of these wave terms. We've already used several of them, but I want to make sure that we had these. All right, so on a typical mechanical wave, you're going to have your amplitude, which we've already discussed. This is the separation between the midpoint and the maximum displacement. Wavelength. Any two consecutive parts of a wave is one wavelength. All right, and we have used this as a wave cycle. We've talked about frequency of the waves and so on and so forth. But wavelength, distance between any two consecutive points. So if we go from crest to crest, that is one wavelength. If we were to go from one trough to one trough, which would be right about over here, that would also be the wavelength. Or we could start here at this position and go to here. That would be one wavelength as well. Any two consecutive parts. The wavelength symbol we would use is a Greek letter lambda. I'll warn you ahead of time, I'm really bad at drawing those, so sometimes my lambdas don't quite look right, but we'll get through that. Okay, and then obviously we have our crest, which is the high point, and the trough, which is the low point. The distance from the midpoint to the crest and the midpoint to the trough should be the same on these waves. Okay, so just a couple of wave terms. Now, here is the difference. We've seen this. This looks like a sine wave. But this is not a position versus time graph. Okay, so what we're basically getting into here, and let's just keep this as simple as possible. Imagine taking a rope and just attaching one end of the rope to the wall. Okay, and you've got the other rope in your hand, other end of it in your hand, and you just start shaking the rope up and down. Obviously, wave pulses are going to move through the rope as it goes towards the wall. So rather than plotting this as the distance left, right, up, down versus time, we are actually plotting what the waveform looks like at a specific time interval. So what we are doing is we're plotting position versus position. So rather than just getting a position time graph that generates like this wave actually is moving and propagating to the right, while the points on the wave are actually moving up and down. Okay, so once again, this is position Y, position X. So this is like you have your string stretched out, and then you give it a snap, and it forms this waveform as the wave propagates. Okay, so this is something that will catch you off guard a couple of times early on in this. Okay, so speaking of types of waves, this diagram here shows a picture of a transverse wave. Okay, so the definition of a transverse wave is like a wave on a string. The motion of the medium, or the actual particle motion, is at right angle to the direction that the wave propagates. Okay, so the actual waveform moves to the right, but the particles that make up the rope, if we're doing this on a string, only move up and down. Okay, so even though the energy is moving this way, if I put a little piece of tape on this rope right here, I would see this piece of tape move up and down and up and down and up and down. It does not move to the right. Okay, so waves on a string are transverse waves. There are several different types of earthquake waves. So the S waves, which are surface waves, those are transverse. And ocean waves or water waves, I put a question mark there because it depends on the physics textbook whether or not they define them as a true transverse wave. Technically, they're not. Really, water waves are circular waves. So if you can imagine, you got a bunch of waves on a pond or a lake, and you're watching them move along, and there's a duck floating in the water. He doesn't just go straight up and down. Water waves are actually circular waves. They move like this. So the energy keeps cycling through in a circular manner. So you don't just see the duck bobbing up and down, you see him moving around almost in a little circle as the wave propagates through, okay? The reason that, like if we're at the ocean, that's why we get the big waves that break, and as it circles around, they end up coming over the top, and then they break when they get close to the shore, because they don't have enough room as the water starts getting shallower and shallower. There's not enough room for that circular wave to form. So it ends up building up and then breaks over the top. So anyway, once again, electromagnetic waves, we're not going to focus on those. That's a Physics 2 topic. Matter of fact, I just finished up the unit on electromagnetic waves in Physics 2. These are considered transverse waveforms or a particle. Once again, those of you taking Physics 2, we'll get into that next year. But once again, these are not mechanical, so they don't require a medium to propagate. Okay, the other primary type of waveform that we have is called a longitudinal or a compressional wave. So make sure you know both terms on this because I'll use them interchangeably and I don't want you to get confused by that. One of the big examples that I can use to explain this, let's say instead of a rope attached to the wall, we have a slinky, okay? Or even just a slinky laid out on a table. And instead of taking the slinky and start shaking it up and down, you instead start giving it pulses along the length of the slinky. So if the slinky's stretched out like this, you're going to give the pulses like this. And now you will have a region where it compresses the slinky, and that compression will move along the length of it. And once again, the slinky doesn't actually move. It's just the waveform that propagates across. The energy propagates in the same direction that the compression is. Okay, so you end up, instead, if you can just focus on one part, and I'll show you something like this later on to kind of distinguish between these, but as you compress it down, that compression forms. Well, if the compression forms here, there has to be another segment where it spreads out a little bit, okay? So a compressional wave is when the motion of the medium is parallel to the direction that the wave travels. So once again, sound waves will be the ones that we're dealing with that. And if you can imagine having a tuning fork, okay, you got the two little prongs on the tuning fork that comes up, and then you strike the tuning forks and it vibrates at a specific frequency, okay, so you get a certain tone off of the tuning fork. The reason that happens is that the two prongs on the tuning forks move back and forth at a certain frequency, and they cause regions in the air that are compressed and spread apart as that sound form radiates outward in 3 dimensions. And so it's really the compression in the atmosphere that generates, and then it gets to us, and then gets to our ears, and then it transmits that signal to our brain to recognize the sound at a specific frequency. Okay, now, this is what a compressional wave looks like in the air. Obviously, if we're going to sketch these, I'm not going to ask you to draw this out, all right? You will see it a couple of different ways. This is one particular diagram. So we have our compressed region and our what's called a rarefaction. So these are compressions. This is rarefactions where it's spread apart. So you have high pressure, you have low pressure with the air molecules. Another way they may represent this is with dots. So they'll have a couple of dots here that are very close together, and then dots get further spread apart and then close together. But instead of drawing 8,000 dots like the picture has, it'll just put them all in a straight line. So that's another way to represent it. An easier way to represent, even though this is a compressional wave, is to draw it like a transverse wave. So the way we represent this in the waveform is these regions where it's compressed, those are the crest, and the regions of the rarefactions, those are the troughs. So notice from this point here to this point here is the distance between two consecutive parts of the wave. So if we diagram this out as a transverse waveform, even though it's not, this would be crest to crest between these 2 points. So it's still one wavelength from here to here. Okay, all right, so I'm going to go ahead and switch on over here in a second. I've got a couple of diagrams here that I'll kind of quickly go through. And then we're going to open up the handout 840 and kind of go through the front page real quick. And if I remember right, that is going to be the end of this segment of notes. So we'll stop right here with this particular segment. All right. When we have two or more waveforms, they will interact with one another, and what happens is they superimpose as they pass through each other or as they radiate outward from the same source. So this is called the principle of superposition, is when two or more waveforms overlap. It would be like having a tuning fork that was a frequency of 500 hertz and overlapping the sound with a frequency of 300 hertz, which that is one of the topics we'll get to later on. What happens is the two waveforms that propagate from those two tuning forks will overlap differently and will have what's called either constructive or destructive interference. Okay, so constructive interference means that the waveforms are in phase with one another. So if the waveforms are in phase at any point, they will add together and form a superwave, basically, which is going to be the combination of the two crests and the two troughs of the waveform that's overlapping. If we have two waves that are out of phase, and I may use the term 180 degrees out of phase, but if we have two waveforms that are out of phase, notice this wave has the crest here and this one the trough here. When we add these two together, we will get what appears to be no energy in the waveform, but the energy is still there, okay? It's just not showing as a displacement from the actual medium, but the energy is still propagating through. It's just a region of destructive interference. Okay, so I'm going to open up 840 here real quick. I would take a few minutes to read through this. This defines principle of superposition and talks about constructive and destructive interference. But I wanted to look at this waveform here and kind of go through what's going on here. So basically what we have here are two waves with equal amplitude, but the frequencies of the two waves are slightly off. If we notice right here at about 7 seconds in this ballpark, so 6.5 to 7-ish seconds, the two waveforms are perfectly in phase with one another. Instead, if we go back here to about 3.5 seconds, we're going to see that we have a wave crest and a wave trough on these two. So if we put these two waveforms together, it makes sense that we have a combination of those two waves. So notice this is double the amplitude, but if we come over here to that 3.5 second range or so, we end up with 0 for the amplitude at this particular point. So this is a waveform that results from the superposition of these two different frequency waves, okay? So I think I'm going to end this video right now, and I'll probably open up a simulation and have another short video just to kind of walk you guys through how this works, and then have you guys work a couple of those practice problems that are in the notes, okay?